Hey guys, welcome back to UK Foundation. This is Kavya. In this video, we are going to do exercise 1.3 and exercise 1.4 of real numbers. Without delaying, let's get started. In exercise 1.3, the questions we have are 6, 7, 10, 11, 12, 13 and 14. The rest questions are related to Euclid's division lemma. So let's get started. Sixth one. If n is an odd integer, then show that n square minus 1 is divisible by 8. First of all, what are odd integers? 1, 3, 5 and so on are odd integers. Now let p equals to n square minus 1. If n equals to 1, then p equals to 1 square minus 1, which is 0. 0 is divisible by 8. If n equals to 3, p equals to 3 square minus 1, 9 minus 1, which is 8. 8 is divisible by 8. If n equals to 5, we get p equals to 5 square minus 1, 25 minus 1, which is 24. 24 can be written as 8 into 3. 8 3s are 24. So this is divisible by 8. So hence n square minus 1 is divisible by 8 where n is an odd integer. They asked us to prove it, we proved. So let's go for the next question. Seventh one. Prove that if x and y are both odd positive integers, then x square plus y square is even but not divisible by 4. Now, how can we write odd integers as 2n plus 1? Let's prove how. Suppose n equals to 1. Then 2 into 1 plus 1, nothing but 2 plus 1, which is equals to 3. 3 is an odd integer. If n equals to 2, 2 into 2 plus 1, 4 plus 1, which is equals to 5. 5 is an odd integer. If n equals to 3, 2 into 3 plus 1, 6 plus 1, 7. 7 is an odd integer. So, odd integers can be written in the form of 2m plus 1. Can they be written as 2m plus 3? We'll check. If m equals to 1, we get 2 into 1 plus 3, which is equals to 5. It is an odd integer. If m equals to 2, we get 2 into 2 plus 3. 4 plus 3, which is 7, which is an odd integer. So yeah, it can be written as 2n plus 3 also. Can it be written as 2n plus 5? Suppose m equals to 1, we get 2 into 1 plus 5, which is 7. Yeah, it is. If m equals to 2, 2 into 2, 4 plus 5, which is equals to 9. 9 is also an odd integer. So we understood that 2m plus 1, 2m plus 3, 2m plus 5, and even if we observe with this and all are odd integers itself. So 2m plus any odd integer is nothing but giving us a resultant as an odd integer itself, where m is a positive integer. Or it can be even negative integer too. If m is an integer, then 2m plus any odd integer is nothing but the form of odd integer. So they are saying x and y are both odd integers. So we'll take x to be 2m plus 1 and y to be 2m plus 3. Both are odd integers itself. Now x square plus y square is. Now we took x to be 2m plus 1. So 2m plus 1 whole square plus 2m plus 3 whole square. Nothing but a plus b whole square. A plus b whole square is nothing but a square plus b square plus 2ab. Now 2m plus 1 whole square can be written as 2m whole square, which is 4m square, plus 1 square 1 plus 2 into 2 4 ab. Then 2m plus 3 whole square can be written as 4m square plus 3 square 9 plus 3 into 2 into 2m, which is nothing but 4m square plus 9 plus 12m. So 2m square, 2m plus 1 whole square plus 2m plus 3 whole square is nothing but 8m square plus 16m plus 10. Now in this you can take 2 common. If you take 2 common, we will get 4m square plus 8m plus 5 into 2, right? So you are having into 2. In the sense this is divisible by 2, obviously then you will get 4m square plus 8m plus 5. If it's divisible by 2, then it is obviously an even integer. So we prove that it is an even integer. Now is this divisible by 4 or no? If we take 4 to be common in this, 8m square can be written as 4 into 2m square. 16m can be written as 4 into 4m. 10 can be written as 4 into 2 plus 2. If we take 4 common, we get 2m square plus 4m plus 2, closing the bracket, plus 2. So this is not divisible by 4. Because 2 is not divisible by 4, you get 1 by 2, right? So this is not divisible by 4. So we proved both. It's an even integer but not divisible by 4, right? We'll go for the next question. Prove that root 3 plus root 5 is an irrational number. This can be done by contradiction. What is contradiction? First we'll assume something and next we have to prove our assumption is itself wrong. So over here we'll assume that root 3 plus root 5 is an rational number. Okay, so we'll take, let root 3 plus root 5 equals to a, where a is a rational number. Root 3 can be written as a minus root 5. We'll square on both sides. Root 3 square is 3 and a minus root 5 square. This is nothing but a minus b whole square. A square plus b square minus 2ab. Over here b is root 5. A square plus 5 minus 2 into a into root 5. Now we'll bring minus 2a root 5 to our LHS and root 3 to our RHS. So 2a root 5 equals to a square plus 5 minus 3. So 5 minus 3 is nothing but 2. So 2a root 5 equals to a square plus 2. Root 5 can be written as a square plus 2 by 2a. Sending 2a to the RHS side. We get this. Over here, we took a to be a rational number. So when a is a rational number, suppose a is 1. 1 is rational number, so we can take a to be 1, right? So if a is 1, 1 square plus 2 by 2 into 1, which is equals to 3 by 2. This is a rational number, right? Now, is root 5 a rational number? No, root 5 is an irrational number. Now, over here, what is this equation saying? Irrational number is equals to rational number. So this is wrong. Why is this wrong? Because we assumed root 5 plus root 3 is a rational number. So our assumption is wrong. This is a contradiction. So the RHS is rational number while root 5 is an irrational number, since 3 and 5 are prime numbers. Hence root 5 plus root 3 is an irrational number. We'll go for the next question, 11th one. Show that 12 to the power n can end with the digit 0 or 5 for any natural number. Do you remember, if any natural number ends with 0 and 5 has the last digit, then it's divisible by 5, right? Divisibility rule of 5 is, if a number is having 0 or 5 at its last digits, then it's divisible by 5. See, 5 into 1 is 5, 5 2s are 10, 5 3s are 15, 5 4s are 20. Now you can observe 5, 0, 5, 0. At last it's having either 5 or 0, right? So this cannot end with digit 0 or 5, in the sense this 12 to the power n is not divisible by 5. That's what it means. So we have to prove that 12 power n is not divisible by 5. How can we prove? Now when we write prime factorization of 12 power n, we shouldn't have 5 to be its factor. If we don't have 5 to be its factor, 12 power n's factor, then obviously it's not divisible by 5. If it's not divisible by 5, 12 power n is not ending with the last digit 0 or 5, right? So now we'll prime factorize 12 power n. How do you prime factorize 12 power n? First we'll prime factorize 12. 12 can be written as 2 into 2 into 3. Nothing but 2 square into 3. Now 12 to the power n, prime factorization will be 2 square into 3 whole to the power n, which is nothing but 2 to the power n into 3 to the power n, right? Now the prime numbers over here, the prime factor is 2 and 3 itself. There's no 5. So if it's not having 5, 12 power n is not having 5 as its prime factor. So obviously 12 power n is not divisible by 5. So as 12 power 5 is not divisible by 5, so it's not ending with digits 0 or 5, right? Since there is no term containing 5, hence there is no value of n for which 12 power n ends with 0 or 5. note it down. We'll go for the next question. Yeah, I'm moving it. 12th one. On a morning walk, 3 persons step off together and their steps measure 40 centimeter, 42 centimeter and 45 centimeters respectively. What is the minimum distance each should walk so that each can cover the same distance? So what should we do to find the minimum distance of like how much should each person walk? We have to find the LCM of 40 centimeter, 42 centimeter, 45 centimeter. So we'll do that. 40 can be written as 2 into 2 into 2 into 5. 42, 2 into 3 into 7. 42 is nothing but 2 into 3 into 7. 45, 3 into 3 into 5. Now LCM is nothing but least common factor. So the LCM of 40 and 42 and 45 is nothing but 2 into 3 into 5 into 2 into 2 into 3 into 7. Right? 2 into 3, 6. 6 into 5, 30. Into 4, 2 into 2, 4. 4 into 3, 12. Into 7. This is nothing but 2520. So the minimum distance each should walk is 2520. So that they cover the same distance at that time. See, the distance varies as one person is taking 40 centimeter step, that long. Other one is 42, other one is 45. So if each walk 2520, so they will cover the same distance in, like, if they are completing their steps, right? We'll go for the next question. Write the denominator of rational number 257 by 5000 in the form of 2 power m into 5 to the power n, where n and m are non-negative integers, hence write its decimal expansion without actual division. So first, denominator is 5000, right? So this one we have to write in the form of 2 power m into 5 to the power n. Prime factorize. There's nothing but, so 2 into 2 into 2 into 5 into 5 into 5 into 5. Prime factorization of 5000. This is nothing but 2 power 3 into 5 to the power 4. Right? 2 to the power 3 into 5 to the power 4. They asked us to write in the form of 2 to the power m into 5 to the power m. Over here m is 3 and n is 4. So first part of the question is done. Next, they're asking us to write a decimal expansion of it without actual division. Now, this can be written as 257 by 5000. We found it can be written as 2 to the power 3 into 5 to the power 4 into 2 by 2. So that will get denominator in the form of 10 to the power something. So 257 into 2 by 2 to the power 4 into 5 to the power 4, which is nothing but 514 divided by 10 to the power 4. 514 divided by 10 to the power 4 is nothing but 0.0514. So without actual division, we found what is the decimal expansion. Yeah. We'll go for the next question. Prove that root p plus root q is irrational where p and q are primes. Same way, it's a contradiction method itself. First, we have to assume root p plus root q to be a rational number. Then we have to prove that our assumption is wrong. So let's assume root p plus root q be a rational number and let a equals to root p plus root q. Now root p can be written as a minus root q. We'll square on both the sides. P equals to a minus root q whole square, which is nothing but a square plus q minus 2 into a into root q. Root q is equals to a square plus q minus q divided by 2a. We are just sending the 2a that side. Over here, a is an rational number. P and q are prime numbers. So over here, overall, this term will give us a rational number itself. Root q is an irrational number. Q is a prime number and root of prime number, right? It's an irrational number. So in this equation, it's saying us a rational number is equals to a rational number, which is wrong. So our assumption is wrong. What did we assume? Root p plus root q is it's a rational number. So our assumption is wrong. So as the right hand side is rational number, while root q This is root cube. Root q is irrational. Since p and q are prime numbers, hence root p plus q root q is an irrational number. Right? We'll go for the next question. Okay, yeah. We are done with exercise 1.3. Exercise 1.4. In exercise 1.4, we have second question, third question, and fourth question. These two questions are related to Euclid's division lemma, so we don't have them. Second question. Prove that 1 and only 1 out of n, n plus 2 and n plus 4 is divisible by 3 where n is a positive integer. Now, let a be n, b be n plus 2, c be n plus 4. Right? Now, they are saying n is a positive integer. Means n can be 1, 2, 3, so on. So we'll substitute n over here. So if n is 1, a will be 1. N is 1, b will be 1 plus 2, which is nothing but 3. N is 1 will get c to be 1 plus 4, which is nothing but 5. So if n equals to 2, a to be 2, b to be 4, and c to be 6. So on till 5 we'll do it. Right? So these are the triplets we get while we substitute n to be 1, 2, 3, 4, 5 respectively. In this triplet, we can observe that over here we have 3, which is divisible by 3. 6 is divisible by 3. Again 3 is divisible by 3. Over here 6, which is divisible by 3. Over here 9, which is divisible by 3. So each and every triplet, we have one number which is divisible by 3. Only one number in each and every triplet. Right? So they're asking us to prove the same thing. We can observe that each triplet consists one and only one number which is multiple of 3. Nothing but when it's a multiple of 3, it's obviously divisible by 3. So this is proved. What did they ask us? Prove that 1 and only 1 out of n, n plus 2 and n plus 4 is divisible by 3. We have been proving it. We'll go for the next question. Prove that one of any 3 consecutive positive integers must be divisible by 3. Now what are consecutive numbers? The numbers which are next to each other like 1, 2, 3, 3, 4, 5 or 2, 3, 4. Right? This can be written as n, n plus 1, n plus 2 itself. These consecutive numbers. So we'll take a to be n, b to be n plus 1 and c to be n plus 2. Over here they are saying again it can be any integer. As 3 consecutive positive integers, so n have to be a positive integer so that we'll get, suppose if n is any integer, we'll take n to be minus 1. A we will get as minus 1. Minus 1 is a negative integer, but they are saying 3 consecutive positive integers. So n have to be a positive integer over here. Right? We'll take n to be a positive integer. Let a be 1, b be n plus 1 and c be n plus 2. At n equals to 1, we get a, b, c to be 1, 2, 3. N equals to 2, a to be 2, b will be 2 plus 1, which is 3, and c will be 2 plus 2, which is 4. So on, so still 6 will do. So these are the triplets we get. These are the consecutive triplets, right? Over here 3 is there, which is divisible by 3. Over here 3, again here 3. If we take n equals to 4, 6. If we take n equals to 5, again 6. N equals to 6, we'll get again 6. This and all are divisible by 3 itself, right? In each and every consecutive triplet, we are getting one number which is divisible by 3. Suppose n equals to 7 we take. We get a to be 7, b to be 7 plus 1, which is 8, c to be 7 plus 2, which is 9. Again 9, this is divisible by 3. 3 3s are 9, right? So we proved that, we can observe that. 3, 3, 3 over here, 6, 6, 6. This and all are divisible by 3. So we proved that in any 3 consecutive positive integers, there will be a number which is divisible by 3. Right? We'll go for the next question. Fourth one, this is the last question. For any positive integer n, prove that n cube minus n is divisible by 6. Let's take a to be n cube minus n. Now we can take n to be common, n square minus 1. This can be written as n into n square minus 1 square, because 1 square is nothing but 1. Nothing but a square minus b square. A square minus b square can be written as a minus b into a plus b, right? So nothing but n square minus 1 square can be written as n plus 1 into n minus 1. So a can be written as n minus 1 into n plus 1 into n. Now they're asking, we have to prove it have to be divisible by 6. If a number have to be divisible by 6, then the number have to be obviously divisible by 2 and 3. This is the divisibility rule of 6. Now if a number have to be divisible by 2, what is the rule? The number have to be even. If the number is even, it's obviously divisible by 2. Or the prime factorization of that number consists 2 to be its factor, then obviously it's divisible by 2. What is divisibility rule of 3? If the sum of the digits of the numbers have to be divisible by 3, then the number is also divisible by 3. For example, we'll take 12. So sum of digits means 1 plus 2, which is equals to 3. So is 3 divisible by 3? Yes. So this number have to be divisible by 3, yes or no? 12 by 3 is nothing but 4. Now 12, we'll write the prime factor of this. 2 into 2 into 3. 2 is there. So this is divisible by 2. Yeah. 6. 2 is a 12. So 12 is divisible by 2 and 3. So this have to be divisible by 6. Yeah. 6 2 is a 12. So it's divisible by 6 also. So when a number is divisible by 2 and 3, then the number is obviously divisible by 6. Right? We know that. Now a equals to what? N minus 1 into n plus 1. Now sum of the digits is n minus 1 plus n plus 1. This is nothing but 3n. This and this will get cancelled. So 3n. 3n in the sense this 3n is nothing but multiple of 3 itself, right? 3 into something. So obviously it's a multiple of 3. So when you divide by 3, you will get it to be n. So this is divisible by 3. We found that. Now this have to be divisible by 2. Obviously, in a consecutive pair of any 3 numbers, one number will be even, right? Suppose 1, 2, 3. 2 is there, which is divisible. 2, 3, 4. One even number is there. So it's obviously divisible by 2. So we found that a is divisible by 3 and 2. So it's obviously divisible by 6. So hence the number n cube minus n is always divisible by 6. Right?